Okay. So first of all, welcome to everyone. This is the third spring seminar of the Statistics and Probability Seminar Series at the University of Nottingham. Today's speaker is Rachel Carrington. Rachel is a member of our group. She's currently a research associate working with other members of the group, in particular Jan Dryden, Simon Preston, Dave Searle, and Willing Lee. Rachel research interests are in high-dimensional data and novel forms of data. Rachel, I want to thank you for accepting to talk in this series of internal seminar. We are very happy to have you here today. This seminar is, as many of you know, is available outside the University of Nottingham. So we are opening the internal seminar to outside the organization. Today, Rachel will talk about semi-supervised word embeddings. Again, before I start, I advise people to mute their microphone. And so, Rachel, the floor is yours.
Thanks. I'm going to talk about word embeddings and particularly a semi-supervised method of approaching them. So this talk is based on my PhD work, which I'm kind of in the process of finishing off. So it's partly joint with my supervisors were Karthik and Simon. So just to give an overview of the talk, so first I'm going to talk about word embeddings and explain what they are and what they're used for. So that will be like the first part of the talk. Then I'll give an outline of the second part, which will be looking at semi-supervised word embeddings and ways to improve the accuracy of the word embeddings that we've generated. So first of all, to talk about what word embeddings are. So essentially, this is just a way of representing a word as a low-dimensional vector. And this is done in such a way that words which are similar or have similar meanings should be close together in the embedding space. So the idea is that we start with a set of documents, which could be newspaper articles as represented here, or they could be books or social media posts or any kind of block of text. And then these are transformed into a set of vectors. So this is an example of what this might look like in 2 dimensions. And the idea being that words which have similar meanings here are close together. So yeah, the idea is that the embeddings somehow encode the word meaning. And just to introduce some notation, so we're going to say that we have p different words in our data set, and we are representing each word by a vector of dimension r, which is quite small compared to p. And I'm using B to represent the matrix of word embeddings, with B1 up to BP being the individual embeddings. So this is just to give a very simple toy example to explain kind of how you would convert this text into vectors. So this is an example of a corpus, which is just 3 sentences. So each sentence is a document. So in order to generate word embeddings based on this corpus, we first have to represent it via we have to convert the corpus into a matrix so that we can use mathematical methods on it. So there are 2 main ways of doing this. We can take the document term matrix. So this is just where we count the number of times each word occurs in each document. So this is what it would look like for this corpus. And this is very straightforward to do, but the disadvantage being that it doesn't take into account where words occur in each document. So we assume that words that occur in the same sorts of documents will be similar in some way, but it might also matter whereabouts the word occurs, especially if you've got a document which is maybe about several different topics. Words which are kind of at the beginning might be different to words at the end. So another alternative is to use the co-occurrence matrix. So if we're counting, two words co-occur if they occur with close together in the text. So we have a window of a certain size. So if we have a window size of 1, the words which co-occur with the word is in blue are just one word on either side. So this and another. If we could increase the window to 2 and get another, the word longer also now co-occurs, but there's only one word in front of it, so we don't get another one on the beginning. And so to get the co-occurrence matrix, we just count the number of times each pair of words co-occur with each other. So this is using a co-occurrence window of 1 for the corpus that I had earlier. So this can contain more information because we're only interested in words that occur close together. And again, we're assuming that words that occur in similar kind of contexts will have similar meanings. So they might not occur. So for example, the words car and automobile, which mean the same thing, they might not necessarily occur close together, because if you've used one, you're probably not going to use the other one, but they'll probably will occur close to the same sorts of words. So they will have a similar pattern in this matrix. So that's the basic idea. And then in order to generate, there are various methods we can use in order to convert this matrix into a set of low-dimensional embeddings. Most of these are based on matrix factorization. So these are some of the popular ones. Latent semantic indexing was the kind of first method, which is just doing essentially singular value decomposition. Then Word2Vec and GloVe are some of the most popular methods at the moment, which use more complicated objective functions and optimization methods, but are doing a similar sort of idea. And so this is just showing that the top two papers are the Word2Vec and the bottom one is GloVe, and these have had a large number of citations, so that this is a very popular area at the moment. So to give an idea of how word embeddings are generated from the matrix, so this is just using singular value decomposition, which, as I said, is one of the kind of simpler methods of doing this. So we want to minimize, so if we take X as our data matrix, and we just want to find the best Rankine approximation to X. And usually we split this matrix into two smaller matrices. So B, as I've said, is our word embedding matrix. A is a matrix of contextual document embeddings that we're usually not that interested in, but sometimes we might be. So in order to split X into A and B, we can just take this Rankine SVD, which split this will give us three matrices, UR, sigma R, and VR, where UR and VR have orthonormal columns and sigma R is diagonal. So in order to split this into two, we can split sigma between the two matrices. So one example is we could take A as UR times sigma to the half, and B as sigma to the half times V transpose. There are other ways of splitting it. For example, we could take sigma R just into A or just into B. But yeah, one way to do it. So yeah, and Word2Vec and GloVe have different objective functions, but again, you're essentially approximating Xij with AI transpose Bj or AB Ij. And these embeddings are used in a variety of applications. So I think search engine indexing was one of the kind of early things they were used for. But they're also used in sentiment analysis. So when, for example, a company is trying to find out people's opinions, like analysing reviews to see if they're positive or negative, to see what people think about them. Machine translation, using word embeddings for different languages, and artificial intelligence is as well an area in which these are used, and there are lots of other applications. So one other question that is, how are embeddings evaluated? So it's quite difficult to tell whether, if you've generated a set of embeddings, you want to know how good they are, which essentially means how well they model language, which, because language is quite a subjective thing, is quite difficult to determine. So essentially we can define a test function G, which is a function of the word embedding set B and some test data, which I've denoted D. The test data is in the form of there are two main types of test data, which are word similarity and word analogy tasks. But I'm mainly going to talk about word similarity tasks because that's more relevant for what comes later at the moment. The idea behind this is we have a set of pairs of words, and these all have a human assigned similarity score. So generally this is, I think in this example, it's a score between 0 and 10 of how similar people think these words are. And it's averaged over the scores given by a number of different people in order to reduce the bias. And the idea is to see how well the word embeddings match the kind of human assigned scores. So we use the embeddings to calculate a similarity score for each pair of words, and then compare these. So so generally this is done by taking the cosine similarity between a pair of words, so just looking at the angle between them. So a smaller angle means a higher value for the similarity. And then, so if we define the human scores as y and the embedding scores as z, we just take the correlation between these two, and that gives us a score between -1 and 1 of how close these two things are. So obviously we want a higher score means that the embeddings are closer to our understanding of language. And there are various different test sets available. So here I've shown the first few rows of the Similax 999 test set, which has 999 word pairs. And there are a few other sets which are commonly used and kind of regarded as the gold standard against which embeddings are evaluated. So then there are also word analogy tasks, which is looking at kind of relations between words, like Paris is to France as Berlin is to Germany. But I'm not going to talk about those here, but there are other metrics used as well. So to summarise so far, so word embeddings are a way of representing words as low-dimensional vectors, and they can be based on the document term or co-occurrence matrix. Most word embedding methods are based on matrix factorization, using different objective functions and optimization methods. And these word embeddings are then evaluated on a set of tasks in order to determine how good they are at modeling language. So in the second part of this talk, I'm going to talk about ways in which we can improve the accuracy of these word embeddings on test scores. So one way to do this is to use you can try using a different word embedding method or using a larger data set. But I'm kind of looking at ways to do this that doesn't involve having to train the model again from scratch. So one way that so this is essentially motivating the semi-supervised approach that I'm going to talk about, which is a way of incorporating some of the kind of human-assigned supervised data into the training objective. So then I'll present some initial results that we've had and some ideas of where we're going to go next with this. So first of all, so improving accuracy on test scores. So this kind of started with, so one way of doing this is to exploit the fact that when you train a word embedding model, there are multiple solutions to this, to the minimizing the objective function. There is not a unique solution. So this is because the training objective is usually a function of a times b. And so we can multiply both a and b by an invertible R by R matrix C. So multiplying a by C and b by C. And this won't change the value of f because this C inverse C cancels out. So we can replace the word embedding matrix B with C times B without changing the value of the training objective. However, this will generally change the value of the test function. So if a test function based on cosine similarity will be invariant to orthogonal and scale transformations of the word embeddings, but not to general non-singular transformations. So most of the time, if you multiply B by a matrix C, this will change the value of the test function. So one idea to improve the accuracy of the embeddings is to generate an embedding set B and then to try to optimize with respect to the test function G over the set of non-singular transformations of the embeddings. So this is something we did in a paper which is shown below. This covers other things as well, but this is one of the things that we did. And essentially this is a sort of two-step process. So you generate a set of embeddings and then do some optimization afterwards to try and improve the test score. But doing this doesn't change the training objective, so it seems like a valid thing to do. But another alternative seems to be that you could incorporate some of this optimization over G into the training algorithm rather than having to do these two things separately. So this is the idea behind the semi-supervised approach. So the idea is you could have an objective function which is of the form some constant times f plus another constant times g, where f and g are as defined before. So yes, so in order to motivate this approach, this theorem says that if we have two functions f and g and define another function h, which is a weighted combination of the two, then if we take the value of x, which minimizes f, and then we find another value of x which has a lower value of h, then this value, the value of g, must decrease. Which it seems intuitive, because if we decrease the value of h, then at least one of f and g must go down. And if f is already minimized, then it has to be g that decreases. So it's saying if we say we start at the value of x, which minimizes f, and we then minimize h, this will decrease the value of g. We're assuming here that both f and g are functions we want to minimize, whereas before we were trying to opt to maximize the test score. So this is sort of 1 minus the test score. So yeah, and there's you can show mathematically that this is the case. Yeah, so also with this approach, we've used multidimensional scaling to kind of give a framework for this, partly because this is a sort of well understood dimension reduction technique, which is similar to SVD but a bit more general. So in multidimensional scaling, or MDS, essentially we are trying to minimize this objective. So the Wij's are weights, and delta x is a function of the data x. So in a simple example, we might just have delta x equals x, and then you're just trying to approximate the matrix x with by the Euclidean distances between well, here the word embeddings. More generally speaking, we can have a non-metric delta function. So, for example, we just specify that if xij is smaller than xkl, then the value of delta xij will be smaller than delta xkl. So this is kind of non-metric because we're only interested in the ordering of the x's and the deltas rather than their absolute values. So, and this is generally used when we have data which is subjective, such as word embedding scores of the human assigned ones, because although we might think that, say, 2 words which are given a score of 7 are more related than 2 words with a score of 5, it's not clear how much more related they would have to be, and people might have their own scales for doing this. So this is kind of relevant here. And we've also looked at using the inner product between the embeddings rather than the Euclidean distance, which is standard in MDS, but most word embedding methods use the inner products. I notice here that we've, instead of AI transpose BJ, we're using BI transpose BJ, which is in order to reduce the number of possible solutions. It reduces some of the non-identifiability problem, and if we have if matrix X is symmetric, then and this is essentially just reducing the number of possible solutions. So as we said, the semi-supervised objective function that I'm looking at is of the form lambda times f plus 1 minus lambda times g. And f and g are both functions that we're minimizing here. So there are several ways I've considered of defining f and g. So f is the unsupervised part of the objective, in the sense that the data in the matrix X is just collected based on, say, co-occurrence data between words, and G is the supervised part because it uses data which is kind of human annotated. So we've kind of assigning a target score between pairs of words. So one option is to kind of just use the multidimensional scaling framework. And so we have a metric MDS as supervised part and non-metric MDS as the unsupervised part. Or we could also do this using the inner product. And another option is where we use MDS as the supervised part of the objective, but then replacing the using MDS as the unsupervised part of the objective, but replacing the supervised part with something more directly related to the word embedding test function. So this is just 1 minus the test function. And so this is, here we're more directly trying to increase the accuracy of the test score by incorporating it directly into the training objective. So obviously we would pick a test set to include as the D for this function, and then choose a different test set to actually evaluate the embeddings on. This is what I've done. So here I've used the word 735-3 test set. So I should say the data is from the Corpus of Historical American English, which contains a selection of documents in different genres from, I think, about 1800 to 2000. And I've used the 10,000, I've just kept the 10,000 words that occur most frequently in this data set. So that's my unsupervised data set X. And then the supervised data set I've used is the WordSim 353 test set, which has 353 word pairs with similarity scores between them. And actually there's slightly fewer than this because not all of the words in the test set occur in the top 10,000 words in my unsupervised data set, so I've excluded the word pairs that don't occur in the other test set, in the large data set. But so I've used this as the D. This is using the third objective function. So this is in the this is the data set I've used in the training objective. And then the plot shows the test scores evaluated on different test sets for different values of lambda. So at the bottom, on the bottom, I plotted minus log lambda, so that the left-hand side is lambda equals 1, which is just the same as unsupervised objective function, which is just doing SVG. And then as you go further right, lambda decreases, so the supervised part of the objective becomes more important. So as we would expect, the test score, that if we evaluate the embeddings on the WordSim 353 test set, the test score increases towards 1, which is what we would expect, consider as this is being incorporated into the training objective. However, the scores on other test sets don't seem to change that much. But so this is probably because the supervised data set that I've used is very small compared to the unsupervised data set. So the unsupervised data set has 10,000 words in it, whereas so it's a 10,000 by 10,000 matrix, whereas the supervised test set has only about 300 word pairs with similarities between them. So it's also sparse in that we only have similarity scores between particular pairs of words. So this means that although incorporating this supervised part into the objective function does increase our test score on the words which are in that set, it doesn't have as much effect on the words that don't occur in that set, or the word pairs that don't occur in that set. So ideally we'd want to do this with a much larger supervised data set in order to have more of an impact on other words in the data set. And in particular, we might want to do this where there's a smaller amount of unsupervised data available. So, for example, in some other languages, so obviously in English, you can have large data sets like all of Wikipedia you could train word embeddings on, but for many other languages, there isn't that much text available in a format that can be used. So in that case, having a modest supervised data set would be an advantage. And also this would be true in specialized applications. So if you're interested in training word embeddings on just say a particular genre, or documents about a particular subject, then you're going to have a smaller data set. So it would be useful to have this supervised data. So although we don't have any maybe the most convincing results yet, I think this is a thing that is worth exploring with some more data. So just to kind of summarize what I've covered. So I've talked about word embeddings and what they are and how they are generated and why we'd want to generate them. I've also talked about how they are evaluated to determine how good they are. And then I've talked about how to increase accuracy of embeddings according to this metric, and some more work that I want to explore in the future. So thank you for listening.